told that, yeah, I am presently a visitor at Raman Research Institute. I am yet to join my next my first postdoc position in China, and waiting for some degree formalities to happen. And by the time I'm working here um, at the nearby institute, which is very nearby to my institute from where I have done PhD, Indian Institute of Science. And yeah, so before that, I did my master's from Banaras Hindu University. And after completing the master's in physics, I joined here and under the joint astronomy program, which is a particularly program focused on research in astronomy. And it contains four institutes in Bangalore. They are a part of it. First is the IISc, which is the host of this program. The other is the Raman Research Institute. Another is the Indian Institute of Astrophysics, and also ISRO. So all the four institutes in the Bangalore, the sister institutes, together host this program. And the idea of this program is that one student get admitted to this program after completing a one-year coursework, which gives a flavor of different fields of astronomy. One is free to choose to work in any of the institutes to complete their research for the next 4 years. So this has been an exciting journey for me. I am working in cosmology, where I try to study the theories behind the evolution of the universe, how it formed and how it is evolving, what the data are suggesting, what new theories we need to explain the data. And yep, this is what I do.
That's really nice, ma'am. Just a reminder to all our participants, kindly post your questions either in the chat or raise your hands after the lecture is over. Thank you. Yes, ma'am, you can continue.
Okay, so I'll now share my screen and maybe we can jump to the talk.
Yeah.
So just a minute. I guess you can see the screen now.
Yeah.
And
yes.
My talk. So yeah, firstly, I would thank the propagation team for organizing this seminar and inviting me to talk on cosmic expansion, which is actually an expertise of my PhD research. So I'll quickly start. So in cosmology, we study about the origin, evolution of the universe and how the cosmic structures that we see, that is the galaxies, clusters, how they form. So initially, this subject was started as a philosophical idea where people had the quest to understand that where did they come from, what is the nature of space and time. But with the advancements in the theoretical physics, for example, from Newton's laws of motion to Einstein's general theory of relativity, combined with the observational advancements as well. For example, when Hubble first observed the galaxies moving farther away from us, and we got to know that our universe is actually expanding. So all these advancements together, the theoretical and observational, have made this field evolve into a precision science where we have a lot of astronomical data today, and we can test our interesting theories of cosmology to understand what is happening in the universe. And one very interesting observation is the observation of cosmic acceleration, which was around in 1998, where we found that the universe is actually accelerating, the expansion is accelerating. And that's when the concept of dark energy emerged, because we do not know what could cause such a peculiar cosmic acceleration. And this would be mostly my topic of the talk today. And where we stand today, so we are still in that quest to understand the nature of dark energy. Still, we are having a lot of observations which are revealing very interesting properties about dark energy still, and we are trying to understand and revive our concepts and of the standard model that we have. So this is the introduction about the talk. So let's start. So we'll begin the story from Einstein. And because this is the general theory of relativity, which actually revolutionized our understanding of space-time and gravity. And it was given in 1915 by Einstein, where he told that actually gravity, space-time are connected, and actually gravity itself is a manifestation of curvature of space-time, where the curvature is actually caused by the energy and matter present in it. So this is very nicely depicted in this diagram and given by Einstein equation, where the left hand side of the Einstein equation, which is the Einstein tensor, is actually quantifies the curvature of the universe, that is the geometry, whereas the right hand side, which is the energy momentum tensor, this gives the source which caused the curvature, which is the energy or the matter present in the universe. And is as very nicely the essence of GR is given by John Wheeler, who says that space-time tells matter how to move and matter tells space-time how to curve. So this is all the pre-Big Bang era, when the expansion of the universe was not discovered. It would be interesting to keep a mind of the timeline of the things that grow, how the theory develops. Now, now in 1915, Einstein gave GR, and in 1917, he tried to explain the cosmology using GR. So he applied the GR to cosmology, and he immediately found that the equations, the Einstein equation, gave dynamical solutions. That is, a universe which was evolving. So this was automatically that he saw from his equations. However, it was the time when people believed that the universe is eternal and unchanging. So this was the prevailing belief. And as Einstein immediately saw that in a universe which has matter that we know that existed, this there would be a gravity force that would try to make the universe collapse. So just to like, because of the prevailing belief that universe should be static, Einstein introduced an extra term in the Einstein equation, which is the cosmological constant lambda, when he applied it to cosmology. And this, the role of this lambda was to create a repulsive force to counteract the attractive force of gravity so that the universe remains static. So this is how Einstein introduced lambda into the picture. And however, these solutions were had their own problems, and later on, the discovery of expansion of universe was there, and then there was no need of lambda. So, and later on, as we will see, I would request you to remember this lambda, because it will emerge as an important part when we will discover the accelerated expansion. Other theoretical developments that were happening at that time, pre-Big Bang time, around 1922 to 1927, the two crucial ones are by the Friedman and Lemaitre, who are actually tried to apply GR to cosmology and work out the non-static solution of the universe. That is, a universe which is actually evolving with time. And these theories laid the foundation of modern Big Bang cosmology. So these are very crucial theories that were built in the pre-Big Bang era. Now, as we know that in 1929, Hubble discovered that the universe is actually expanding. What he observed, so he observed the velocities of distant galaxies. And this left-hand side is the Hubble's original plot from his paper, where the y-axis contains the velocities of the galaxies, and the x-axis is the distance from to the galaxies from us. And these are the data points. And we found that there is a linear relation, that is, the velocity is directly proportional to the distance. That is, the farther the galaxy from us, it is moving with more speed. So this relation, that B is proportional to D, and H naught is a proportionality constant named after Hubble, the Hubble constant, and it is a measure of the present expansion rate. So this event was the observational evidence of Big Bang theory. So yeah. So what is this Big Bang theory? It says that our universe had a beginning. So it started from an initially hot and dense initial state, and it is going expansion since then. And how to understand the expansion, like, there are some technical terms that would appear later on when we'll discuss about cosmological models. So you can consider this like you have a fixed coordinate system, like the right hand side shows the coordinate system. You can see the cursor, right?
Yeah, ma'am. It's
Yes,
Okay.
we can.
Thank you for confirming. Yeah. So to understand the expansion, it's like you have a fixed coordinate system which actually expands with time, and you can write it as like a physical distance here, which is a distance scale factor multiplied by a fixed coordinate distance, and this is scale factor actually tells how much the coordinate system itself has expanded with time. And the expansion rate, which is the Hubble parameter, is actually the rate at which this scale factor changes. So the physical distance are increasing, but you can consider that you have a fixed grid system or coordinate system, which is expanding with time. So this is a view of how you understand expansion in a Big Bang theory. And Hubble parameter is a very crucial parameter in cosmology because it contains important information about how this rate of expansion changes with time, which will be helpful to us to calculate the distances to the distant galaxies, as we will see later. Now, at this point, I will also introduce cosmological redshift. And so cosmological redshift, so as the Big Bang theory says that the universe is expanding. So as the universe expand, for example, you see on the right hand figure, the wavelength of the light that is coming to us is actually stretched because of the expansion. And when the wavelength becomes longer, it falls to the redder side of the electromagnetic. Hello?
Yeah.
Okay.
Yeah, ma'am. Yeah, ma'am.
Okay, okay. Okay. So it falls to the redder side of the electromagnetic spectrum. Okay, so that's why we say that that's why the redshift is a measure of how much the light has been stretched because of the expansion of the universe. For example, how we observe, so when we observe the spectra of galaxies, there are some particular absorption lines that we observe. However, because the light is coming from far away, these wavelengths get shifted towards the red part. As you can see, the whole pattern is getting shifted towards the red part, and that is what we meant by redshifted. And higher the redshift, it indicates that the light is coming from farther and farther away. So this is the cosmological redshift. Now, interesting discovery of 1998 was when two separate teams independently observed the type 1a supernovae, which are very important entities in cosmology, and I will discuss about them in the next coming slide. And they used these supernovae to measure the cosmic expansion history. And what they found is that we already knew that the universe is expanding, as you can see in this left bottom figure. However, the observations reveal that the present expansion is actually accelerating. That is, the expansion is happening at a very faster rate than expected. And because of this, that means there is some repulsive force to counteract the gravity, which is leading to even faster expansion. Because if matter is present, it is assumed to gravitate and hinder the cosmic expansion. However, if the expansion is happening really faster, there should be some repulsive force which is causing the universe to accelerate faster. And that is when the dark energy term was coined to explain this mysterious force that no one has thought of before. And this is what also got the Nobel Prize in 2011. So now coming to type 1a supernovae. So these are powerful explosions of white dwarf when they are in a binary system and accumulating mass through the companion star. And when the mass limit reaches a particular critical mass, which is also called the Chandrasekhar mass, they explode, giving a thermonuclear blast. And this explosion, what is the property of this explosion? So as this white dwarf explodes, the luminosity of it initially rises and then falls. So it has a definite light curve. Now, what is interesting is that because the phenomena that causes this explosion is same, so that's why the different supernovae have the nearly same peak luminosity, and that's why they are called as objects of standard candles, because we know their intrinsic brightness or their absolute luminosity. So how do we use these type of standard candles to infer distances? So it's like when we observe a supernovae, so we are actually measuring the flux, that is what is the apparent brightness of that object. So once we know the flux which is observed, and because we can calibrate the absolute luminosity, which is because we know how the supernovae actually form, so we can infer a distance from them. So it's like the flux and luminosity. Once you know both of them, you can infer what is the distance of that object from us. So this is how the distances are measured using the type 1a supernovae. So what And distances, as I will again and again emphasize in my talk, that distances play a very crucial role to understand what is the cosmological model of the universe. So what do we observe? So we are observing various supernovae at different redshift and what is their apparent brightness. So you see in terms of data, so it's like we have a redshift on the x-axis where 0 represent present and the rightmost represent the higher redshift, that is the in the past. And on the y-axis is a measure of brightness. And we observe this, so this gives a brightness gives a handle over the distance to the object. So we have a distance redshift relation. And whenever we have a distance redshift relation, we can connect it with the theory of the cosmological model that I will discuss how this actually happens. So what was observed is that there are some supernovae that appear to be dimmer than expected. And if they are appearing dimmer, that means they are traveling more distance than what we expect. And that means the universe is expanding much more faster, that the light from them is more stretched and they appear to be dimmer. And that would be the reason of dark energy. This is how they initially thought that about the accelerated expansion. Now, if you see the data points here, the red one are the data points, and the blue are the different theories. For example, this one, the dashed blue one, is the universe which does not have dark energy; it just have matter. Whereas the top one, the solid blue line, is a case where there is a dark energy also present. So we find that this theory gives a good fit to the data, and this is how we test our theories. We have different theories, we get the data, we check the predictions of the theory with the data, and then data tells us that which is the correct model, cosmological model that explains the universe. And this is how we observe that the universe is actually accelerating, and there is some other component called dark energy, which leads to this acceleration. So this is the picture that we have. So we have a Big Bang, after which the universe has been expanding since then. And there are various crucial cosmological epochs during this evolution. And very recently, the universe has entered into a phase of dark energy domination, where the expansion has actually speeded up. It has become accelerated at very late times. So, and this would be our present focus of this talk. So now let's talk about the model. So as of now, we have discussed the data part, that what laid the foundation of Big Bang cosmology as well as the dark energy models. Now let's talk about dark energy accelerated expansion. Now let's talk about what is the model of cosmology. So the in modern cosmology is built on two key ingredients. First is the cosmological principle. So what this principle says is that if you look the universe on very large scales or the cosmological scales, then it appears same at all in all direction and at all points. So this is called the principle of homogeneity and isotropy. And this is a principle that has also been confirmed from various observations, like from the observations of cosmic microwave background, which is the relic radiation from early universe. We find that this radiation is almost homogeneous and isotropic in every almost same in all the directions. And similar, this principle has also been confirmed from our large scale structure surveys. For example, this is an image of how a large scale structure survey look like. This is called cosmic web. So here the bright points are the galaxies and the darker points represent the void. And if you see it from on large scales, you see that it looks the same in all the directions. So this symmetry, this simplifies the calculations for us, and the metric of the universe, which is the Lemaitre-Robertson-Walker metric, encodes this symmetry of the universe, that it looks same in all the directions, where this is scale factor, which is the same, which encodes the information of how the universe, how the physical distances are increasing. So this represents this information is very nicely encoded in a simple metric. And this metric contains essential information about the curvature or the geometry of the universe, which actually gives the right-hand side of the Einstein equation. So we have a cosmological principle, a symmetry which simplifies calculations for us, and which is something that we also observe. The other ingredient is how the geometry will change, and that for that we need a theory of gravity, which is the general relativity, which tells us how matter or the energy in the universe uh, will change the geometry of the universe. So, which is given by the Einstein's equation, where the left-hand side is something that is figured out from the metric, and the energy momentum tensor is corresponds to what are the constituents of the universe. So these build on these two foundations. The theory is as follows. So there are three crucial equations that we will talk about. So these are called the Friedmann equations. The first two are the Friedmann equations, which are obtained by combining general relativity with the FLRW assumption of the metric. And they tell us about how the scale factor evolves with time. So the first Friedmann equation is given as follows, which shows that the Hubble parameter, that is the expansion rate of the universe, is directly proportional to the energy density, total energy density of the universe, where the total energy density could have contribution from radiation, matter, or dark energy, whatever is present in the universe. And the second Friedmann equation, this tells us about the rate of ex, um, whether the universe is expanding or decelerating. So rate of expansion. So, and in this equation, we see that there is a role of the pressure of the fluid as well, which also decides that whether the acceleration would be, whether the rate of expansion would be accelerated or decelerated. Third one is the energy conservation equation. Because we are in an expanding universe, so the energy conservation equation is modified for different fluids, and the fluids are defined with their equation of state, which is a ratio of their pressure to the energy density. And as the universe expands, the energy density of the fluids will dilute depending on a rate depending on its equation of state. So keeping in mind these three crucial equations, which lay the foundation of background cosmology, we can move forward and talk about that what causes accelerated expansion, because we are trying to focus on the dark energy component. So as I discussed, that it is the second Friedmann equation that tells us about whether the expansion would be accelerated or decelerated. And once you do some mathematical calculation, that accelerated expansion requires that the double derivative of the scale factor should be positive. It leads to a condition that the equation of state of the fluid should be less than minus 1/3. Now, this means that acceleration requires a fluid with sufficient negative pressure to counteract the attractive force of gravity to give the accelerated expansion. So this is what is an essential condition that you should keep in mind while we go along in the talk regarding the condition for the accelerated expansion. Now, let's talk about what constitutes the universe. We know there is radiation. There is cosmic microwave background radiation that was observed firstly in 1965, and we have precise measurement of cosmic microwave background radiation and the small fluctuations in it. There are neutrinos, and these are relativistic particles which have an equation of state 1/3, and therefore the energy density also dilutes as 1/A4, where A is the scale factor. At this point, keep in mind that scale factor, as the universe expands, it means the scale factor is growing with time because the size of the universe is increasing. So scale factor essentially encodes the information about the size of the universe. So then there is matter. So matter includes two components. One is the baryonic matter that is visible to us, and the other is the cold dark matter that is not visible to us directly, but we infer it from its gravitational effects. And both of them being matter, they are pressureless. They follow the property of being pressureless, and their equation of state, their energy density also dilutes with time with time as the universe expands, with following a scaling 1/AQ. However, it is important to note here that in both the cases, the equation of state does not satisfy the condition for accelerated expansion, and that's why these components actually decelerate the universe. So the expansion is happening, but it will slow down with time. The rate of expansion will slow down with time. And therefore we need a dark energy component to explain the accelerated expansion observations. So what is dark energy? We don't know much about it. We just know that it is some fluid that should have an equation of state that should be less than minus 1/3. A very simple case that can happen is a cosmological constant. And I said that initially Einstein introduced this to make the universe static so that it opposes the attractive force of gravity. It is like a repulsive force which to oppose the gravity. And this is a very simple case with equation of state -1. So it satisfies this condition and a property that its energy density remains constant in time. So this is the same lambda that was initially introduced by Einstein for some other purpose to make the universe static. However, this same lambda can lead to an accelerated expansion, which can explain the present um, observations. So with this, I will introduce you the standard model of cosmology that we call, which is the lambda cold dark matter model, where lambda stands for cosmological constant, CDM stands for the cold dark matter. And this is the concordance model. Why? Because it fits all the observations very nicely. It is a very simple model. So when we say we have a cosmological model, we can write how the expansion rate of the universe looks like in that model, which is given by the first Friedman equation. Now here the expansion rate for the lambda CDM model. So the expansion rate is proportional to energy density, and energy receives contribution from matter, from radiation, and there is a contribution from dark energy given by rho of lambda. And we can write the expansion rate in a very convenient form that we see in our textbooks, where these different omega are the fractional contribution to the total energy density at present of the different components. So M for matter, R for radiation, and lambda for dark energy. And once we know a model of expansion rate for a given cosmological model, we can infer the distances at different redshifts. So we can predict from theory what would be the distance at a given redshift. And this is how we link the theory with the observations. The observations also give a handle of distance at different redshift, whereas from the model also we can predict them, and comparing them we get to know that whether our model explains the data or we need to move to a different model. So once again, why concordance? As I said, that because it is the simplest model that fits all the observations. And the three very crucial observations in cosmology that we have: first is the cosmic microwave background. The other is the large scale structures, about which I will talk later. So large scale structure surveys give you the distribution of galaxies. It traces the distribution of galaxies. And in this distribution, this trace, we have crucial information about the cosmological model, that how the universe is expanding. And the third one, as we discussed earlier, is the type 1a supernovae. Now, what we do in cosmology, we combine all the data sets, we try to fit it with the models and try to find the best fit parameters that explain our universe. For example, combining these three observations, we get some numbers like omega m, which is 0.3, omega lambda, which is 0.68. And this is how we interpret that around 68% of the universe energy budget is dark energy, 27% is dark matter, and 5% is visible matter. So this is about the standard model of cosmology, which is the lambda cold dark matter model. Now, the question one can ask is, can dark energy be dynamical? Because we considered the very simplest case where the equation of state of dark energy was -1 and its energy density was same throughout. It does not evolve with time. That is the simplest case. Now, the question is, can it be dynamical? That is, can its energy density evolve with time? So yes, why not? Theory-wise, yes, everything is possible, because we know that the only condition that we require for accelerated expansion is that the equation of state should be less than -1/3. And from energy conservation, this equation represents the energy conservation. We see that if the equation of state is other than -1, is not equal to -1, there would be an evolution in the dark energy density with the redshift. That is, the dark energy density will change with time. And that is what we call the dynamical dark energy. So for example, two cases that are widely studied in literature are like, we are going from constant lambda equals to -1 to something else. So we call it a W CDM cosmology, where W is not equal to -1. So, but here we have one extra parameter W. Now we want to test these two. So what happens is we have different models and we again test the models with the data to find the best fit values. So this extension from the simple lambda CDM model brings about extra parameters. For example, WCDM, one extra parameter. Then there is other case which is called the W0 WA CDM cosmology, also called the CPL parameterization. Here there is an evolution in the equation of state. There are two parameters, W0 and WA. So again, the theory becomes a bit complex because of an introduction of two extra parameters in the theory. Then the question one can also ask is that how do we theoretically motivate these models? For example, here these are just parameterization. We are saying maybe the equation of state is something else than -1, or it has some evolution. But what is the theory? Can we explain it from the fundamental theory that how this behavior actually arises? So yes, there are a lot of theoretical frameworks to discuss various evolution of this equation of state. There are quintessence dark energy models where dark energy behaves as scalar field. There are interacting dark energy scenarios where people talk about dark energy interacting with dark matter. And there is also modified gravity dark energy where people talk about working in a framework other than general relativity. General relativity is the simplest gravity theory. However, there could be other gravity theories in which one is free to work with. So there are various phenomenology. If someone is interested for advanced topics in dark energy, one can go to this book. This is a very nice compilation of the different models that have been studied till now in dark energy. But now, after talking about the models, let's talk that why do we need dynamical dark energy? Because we have a very simple model and very simple, elegant model, which could explain most of the observations. The answer is that as we are advancing in technology, our instruments are improving in their systematics. The data accuracy and precision is getting improved. Because of this, there are certain emerging tensions in the field, which are called cosmological tensions. And what these tensions mean, so there are some observations which are inconsistent with the theoretical prediction of our standard model. And that's why they are creating a challenge for the standard model um, to explain the the newly coming observations. This is what is tensions. So there is one very famous prevailing tension in cosmology that is called the Hubble tension. However, this is not my present topic for the talk. And if someone is interested, we can discuss lightly in the discussion session. So this is a prevailing tension. However, what we are interested today is these recent hints of dynamical dark energy from daisies. So DAISY is a new observation which has given hints that the dark energy may be dynamical, that is, it could be evolving in time. So we will talk mostly about this observation. So what is this DAISY? This is dark energy spectroscopic instrument. This is a ground-based telescope which is situated in Arizona, and it has been operational since 2021. And what it does, it observes millions of galaxies and quasars, spanning a redshift range of 0.1 to 3.5, and it has given the largest 3D map of the universe, tracing these galaxies. And it is a 5-year plan. It is still going on. They have released the two sets of data as of now. And what are the scientific objective of this mission? Firstly, to measure the expansion history. As we will discuss later, that this trace of the large-scale structure contains crucial information that how much dark energy is present in the universe, how much dark matter is present in the universe, and that thereby it can constrain the underlying cosmological model. Next, it can measure the growth of cosmic structures. That is how the growth actually progresses with time, the small density fluctuations which eventually grow into structures, how that evolution happens. And with these, it can test the nature of dark energy, as we will discuss later. That is, it has already hinted towards a dynamical nature of dark energy, and it can also test the nature of gravity on cosmological scales, whether this is just GR or we need to go for modified gravity theories. So this is the dark energy spectroscopic instrument. Now let's talk about the buzz that is around and that has created a very strong sensation in the dark energy community as at present. That is, the observations of DAISY have hinted that the dark energy is evolving. Till now, we were very happy with the standard model of cosmology, where the lambda was just a constant, so dark energy was just a constant with equation of state -1. And this model gave a very nice fit to all the observations. Now, after DAISY, there are challenges to this model because we find that the evolving dark energy models, like one parameter or two parameter models, are giving a better fit to the data in comparison to the standard model. So interested people can go to the official web page of DAISY. All these images I have just borrowed from there. So the press release, so there are a lot of press releases, as you would have seen in news, that talk about that dark energy getting weaker, dark energy other than -1 and all this. So these are interesting articles which describe for in a layman language that what they are observing from these data. Now we'll talk about that how actually DAISY proves the nature of dark energy, and that happens by measuring the expansion history because it contains the information of expansion history, that is h of z, which in turn depends on the underlying cosmological model, whether it is standard model, whether it is some other model. And how expansion history is captured? It is captured by a phenomena called baryon acoustic oscillations. This is what we will discuss now. So baryon acoustic oscillations. So what happens is that when the universe, in the very early universe, when it was very hot and dense, photons and baryons, they were tightly coupled to each other and they formed a single fluid. And small density perturbations of this fluid, they propagated like sound waves. So they propagated like sound waves. Now, as the universe was expanding, it was getting cooler. So there was a time called a recombination epoch, which happened around 3.8 million years, 3.8 million years after the Big Bang, when the universe cooled enough such that the baryons, like the protons and the electrons, they combined with each other to form the hydrogen atom, and the universe became neutral. And the photons and baryons stopped talking to each other, and photons traveled freely to us, and we observed the cosmic microwave background. But what happened to baryons? Baryons were left where they were at the point of recombination. This is an artistic view. The leftmost image is an artistic view of the how this density wave would have propagated. So once the recombination happens, the baryons stalled there, and this left a characteristic scale, as you can see, in the distribution of structures. Later, what happened? These density perturbations, they grew, and a lot of galaxies emerged in these places. However, the actual galaxy survey is very different from this artistic view. This looks something like that because a lot of galaxies have formed by the time of recombination till now. Now, this is scale, the characteristic scale, which was actually the length that this density perturbation has traveled from Big Bang to the point where the photons decoupled. This characteristic length scale is hidden somewhere inside the large scale structure survey, and which could be inferred in a statistical manner. How? We can find 2-point correlation of the galaxy correlation function, which gives a measure. So here is how we statistically infer this characteristic length scale. So we find the number of galaxies. So on the x-axis is the measure of distance, on the y-axis is the probability of finding galaxy pairs separated by a given distance. And in this way, you see that this function follows a behavior. The number of galaxies, as you go farther away, this correlation would decrease. However, there appears a bump which corresponds to this hidden characteristic scale in the cosmos, and this is what is known as the BAO peak. Now, when we are observing large-scale structure surveys at different redshifts, we obtain this BAO peak. And that's why BAO gives a measure of expansion history. So we observe this BAO peak, and we know that the characteristic length scale, what it would be, that's why it's called a standard ruler. So it's like we are observing a standard ruler at a given redshift, which gives a handle of the distance to that ruler. So again, we have a distance measurement from baryon acoustic oscillation at a given redshift because of the BAO phenomena, which gives a standard, which behaves as a standard statistical ruler. And this standard statistical ruler, because we know that how density perturbations propagate in early universe, this could be calibrated from theories, and this has a value around 150 megaparsec. So this BAO peak then gives a measurement of distance. So you again have a distance at different redshift, and that's why you can constrain the underlying cosmological model using this observation. Now I'll jump to what are the highlights of DAISY. So the DAISY observations, what they suggest is that there is a preference of dynamical nature in the dark energy models and in comparison to lambda. So for example, here is a plot from one of the papers which have done extended analysis from the DAISY results. So the dashed line is the lambda CDM case where the y-axis is the equation of state of dark energy and the z-axis is the redshift. And you see that they have worked with different parameterizations and where the equation of state varies in different way with redshift. And they find that in all the cases, the data prefers an evolving nature of dark energy, where at present time, that is at z equals to 0, the dark energy equation of state is actually less than -1, which falls in the quintessence regime, which is where the energy density of the dark energy gets weaker or it dilutes with time. So if you read in the press that the dark energy is getting weaker, it means that the present equation of state is less than -1. Sorry, it's greater than -1, and it dilutes as the universe expands. Now, there are other peculiar features in the data that this evolution indicates that the equation of state actually is less than -1 at high redshifts. So at high redshifts, most of these curves fall below W equals to -1, which again is something which is creating sensation in the cosmology community because this leads to a phantom kind of behavior. And the phantom behavior is something where the dark energy density increases as universe expands. So this is a peculiar feature which cannot be explained in various standard theory, particularly the standard cosmology, where we work in the general relativistic framework. So this is the observation which has been a very interesting from the last few months. So now another highlight. So you might have seen these plots also in the articles where this W naught WA model, which is the CPL model, which actually gives the best fit to the DAISY and the combined observations. So this plot shows the preferred region of the parameter space of W naught WA from the predictions of the data. So, and this again, this image is borrowed from one of the articles from the DAISY collaboration, where they try to explain what this technical plot actually means for everyone. So on the right-hand side is an explanation where you see that firstly, this is from 3 observations: DAISY, which is the large-scale structure observation; CMB, cosmic microwave background; and DES, which is a supernova dataset. So combined with the 3 observations, which I discussed are the crucial observations in cosmology, they get this plot. And this dark inside contour indicates the region where the data predicts that 68% of the values of with 68% confidence level that the values of W naught and WA would lie. And the larger outer curve indicates that the 95% with which the data says that W naught and WA would lie in this regime. What is interesting is that the point corresponding to lambda is here, where you see a star where W naught equals to -1 and WA equals to 0. So if you put W naught to -1, WA to 0, this is the case of constant lambda. And you see that the data is actually, the predictions from the data are actually quite far away from the lambda, which means that now the lambda CDM model is not a very good fit to the recent data. So now with this, I think I have come to my end slide where we talk about that what next. So firstly, the conclusion. So lambda CDM has remained very successful in explaining a lot of cosmological observations. It is very simple. It is consistent with many data sets. However, these recent DAISY results, they have challenged it because there is a prominent hint of dynamical dark energy from this observation. And there are also peculiar features like phantom crossing and phantom-like behavior of equation of state, which cannot be explained in a general relativistic framework without instability. So the key questions that are here that are now present is that what is the theory that can explain dark energy? Could modified gravity explain it? Could interactions explain it? Or what else? However, a perspective on this is that this is the present talk where we have discussed is based on the background expansion history. So there are other crucial information that are hidden in the perturbations. That is how the small fluctuations grow to form the large scale structures. And there are various observations that are working to collect data and interpret information about the growth of structures. And these data will contain additional information about the nature of dark energy. So as of now, we still are in doubt what should be the right model of dark energy, and we look forward to upcoming large-scale structure surveys like the Dark Energy Spectroscopic Survey, which is still ongoing. DES is ongoing, Euclid is ongoing, LSST will be soon operational, and these will give us new insights about the true nature of dark energy and gravity on cosmological scales. So this is just about my research work. So my works I have focused on cosmological tensions like Hubble tension, the what should be the model of dark energy, what modified theory gravities can actually help us reconcile some of the cosmological tensions. These are my collaborators, and yeah, with this, I think we can have the questions now. Thank you.
Thank you, Yashi. It was really a very wonderful talk. I think
Thank you.
so. For people like me who are a layman in physics, I really didn't understand. I'm sorry, the part of the equation. I'm really sorry
Hmm.
for that. But yes,
That's
it's
fine.
my
That's
fault.
fine.
I am not a student of physics, but yes, the theoretical part which you explained was really nice, really, really nice. So
Thank you.
I go on with the questions. I first read out the questions in the chat. The first
Sure.
question is asked by Pratyush Singh. Ma'am, what is a Hubble parameter?
Okay. So as I already discussed in the initial slide, so Hubble parameter is a measure which tells us how fast the universe is expanding. So as we can see that we can define a scale factor with which the distances will actually increase with time, and how this scale factor evolves, that how fast the expansion is happening is a measure that we get from Hubble parameter. The rate of expansion of the universe is what we get from Hubble parameter.
Okay. The next question, Harshita is asking, how does the Hubble constant explain the expansion? How does it explain
How does it explain the expansion?
expansion of the universe?
Expansion of the universe. Okay, so Hubble constant is a constant. So expansion of the universe is something we observed from observing the velocities of the galaxies that were at some distance. So this is the observation, and H naught is a like a constant. It's like you observe a relation that V is proportional to D, and you introduce it as a constant named after the scientist who developed this relation. So when you say that we observe, how we know the universe is expanding, it is from the observations of galaxies at some distance and observing their velocities. So this is how to answer that question, I think.
Okay, okay. The next question is from Nawaz Khan. Ma'am, what is the nebula rose? Please explain.
Okay, so these are some very early galaxies that I would say, which
Okay,
Hubble observed at that time.
okay.
Young galaxies, yeah.
Yeah. So the next question, what impact on the universe would dark energy model have? If it's static or dynamic, how would it change the properties of the universe?
Okay, so you're asking the question that what if the dark energy is dynamical? So
Yeah.
there could be, so yeah, so interesting, yeah, that is what we are trying to understand from the large scale structure surveys. So if the dark energy is dynamical, the evolution of the universe. For example, if the expansion rate would change in comparison to lambda. For example, we are saying that dark energy is getting weaker because the dark energy density, if it is dynamical and if the equation of state is greater than -1, then the dark energy density will slowly dilute and the acceleration will not happen that faster in comparison to lambda. Also, what would be interesting is to see how it affects the growth of structures. That is, does it cause any difference in the how the structures grow at late times? This is something that could be different from the standard model if the dark energy is evolving or if it is interacting with other dark sector.
Okay. So, Yashi, you mean to say that the dark energy, what I understand is that dark energy is the reason for the gravitational lensing which we see in the photographs of Hubble and JWST.
No, it's not completely the reason that it's a dark matter mostly, but yeah, dark energy can have contribution if it is coming from some other theory, for example, modified gravity theory or some interactions with the dark sector. So yeah, in comparison to the standard model, if the dark energy is something else which is evolving, and actually the idea point is that at this point we don't know what actually is the model, whether it is an interacting dark energy, whether it is modified gravity, which is an open question as now, and we wait for these other observations to come to us and help us sort our way out. So yes, there could be significant changes in these observations once dark energy is something else.
Okay. So Joseph is asking, if asked by a layperson, what is the importance of knowing about the cosmological constant, dark matter, dark energy, etc.?
Okay, so it's like if you want to understand how the about the theory of the universe, so you need to know that I mean the structures that you observe. So you need to know that how they form. Like if there was no dark matter, the for example, the image that we see, if the dark matter was not present, this would be really different. And that is what we see in our theoretical predictions of n-body simulations. We can make any theory and then confront it with the data. So it's just a quest to understand that what we are observing is, are we able to interpret with our theoretical knowledge of physics that we have? So yeah, that's
So
what.
you mean to say that dark matter or dark energy is the thing which is there in between the planets, in between the
It's
empty
everywhere.
river is there.
It's
It's
everywhere. Yeah.
it's everywhere. So
Yes, it's everywhere.
the distances which we see is basically
Yeah.
the dark matter and the dark energy.
Yeah, it depends on the composition, like how much is the dark matter, dark energy. When we talk about the cosmological distance, with very large distances, at which the expansion of the universe is actually, one can feel the expansion of the universe. So it depends how much is, for example, when we say that we have 68% dark energy, we have 27% or 30% of dark, the total matter. These constituents are important to have an idea of what would be the distance to a given redshift. So the constituents play a critical role to shape in the cosmological model. Once, if you don't know that there is dark matter or dark energy, you will definitely calculate wrong distances to the objects and infer them incorrectly. So there is, yeah.
Okay, okay. Uh, Another question: could you think we can be able to find the secret of unlimited universe by limited sources we have?
Okay. So, yep, being person working in like data analysis and the theoretical like blend of both of them, I am very positive and I look forward to upcoming data sets to tell us more and more, and we theoreticians are ready to explore our mind to build up, to come up with new ideas and think of what maximum information we can get from whatever we are observing.
Yeah.
So yeah.
So, Utkarsh Kumar says that you mentioned about a library star supernova. Sorry, binary star supernova. So,
Mhm.
are there any three body system in supernova or multi-star system?
Not that I'm aware of. but I may not be the expert to comment on this question, but not that I'm aware of. I have heard
Okay.
of binary systems.
Yeah. And the next question is, if the universe is really accelerating due to dark
Hmm.
energy,
Hmm.
how does Hubble parameter change
Hmm.
over time?
Okay, so this is something that you can work out. Hubble parameter will actually increase with time if the acceleration is happening. But yeah, these things you can work out from the equations as well. So h square is proportional to the energy density. So if the how this dark energy density evolves will directly affect the evolution of h square at very late times. Yes. So if the universe is accelerating and yeah.
Okay. So the next question, how does dark energy drive the accelerated expansion of the universe currently observed?
How does it drive currently observed? Okay, so this is what the observations are telling. So when we say that we are observing dynamical nature of dark energy, we are using all the observations, using the supernova as well, which gives us all these observations are that giving accelerated, indicating accelerated expansion. So this information is already there, and when we say that we have a model which explains this data, so this is a model that also explains accelerated expansion. So
So
I
do you mean to say that as the universe is accelerating, as it's expanding more and more, so the
yeah.
amount of dark energy and dark matter are also increasing?
Dark matter will actually decay. So it depends on, so it boils down to the equations again. So the equations tell us how the different components will actually evolve with time. That is the different fluids. Now it depends on their equation of state. That is what is their equation of state. For example, dark matter, which is pressureless, it dilutes. So it's like the density decreases as universe expands because the size, the volume is increasing. So for dark matter, surely it will dilute that energy density will decrease, but for dark energy, which is again interestingly, we don't know what is the equation of state, so we get some inference from the data that the equation of state of this dark energy is evolving or constant or whatever. So the energy density of dark energy will depend on the equation of state. So
Okay.
the answer is for dark matter, it will dilute the contribution to the total energy density will decrease because it will dilute, whereas dark energy, it can increase or decrease depending on the evolution of the equation of state. If it had
So,
been lambda, this energy density would have been constant.
so you mean to say that there is a finite boundary for the universe? like
I
like you say that if it is expanding more and more, the
Mhm.
dark
Mhm.
energy and the dark matter will
Right.
dilute.
Yeah.
So
So these
dilute.
are dilute. Dark energy, dark matter will definitely dilute.
Yeah.
So the idea is that yeah, one can extrapolate to like once you observe that the universe that for example, I'll just come to this plot. For example, this is the behavior of the equation of state. Now you can extrapolate it what will happen in future. If the equation of state keeps on increasing from -1, then there may be a time when the accelerated expansion even may even stop. So there could be an extrapolations where we will say that the dark energy is getting weaker, and if it is getting weaker, then maybe there would be a state when the universe will stop accelerating and rather start contracting. So these are some extrapolations that would be obtained from the data, but not now. These are the extrapolations which can happen in near future
So
also.
that means the theory, the proposed theory of the big crunch and the big freeze, the dark freeze, is can be true.
Yeah, we need to. Okay, so yeah, I would stay tuned for this to have
I,
more.
I'm really sorry. These are my questions. Actually, these are not
No,
the
that's
questions
fine.
from the chat.
No, that's
I
fine.
get curious and I get sorry. Coming back to the
But
chat questions, what
yeah,
are the
sure.
key differences between dark matter and dark energy? A very simple but yes,
Yeah.
yet complicated question.
Firstly, dark matter behaves like ordinary matter. Just we can see it, so it gravitates. It will not cause accelerated expansion. It is like an attractive gravity force. So whereas dark energy is opposite to that, it counteracts gravity. It's an repulsive force that leads to expansion. So this is the primose difference between, I would say, dark matter and dark energy.
Okay. So the next question, is dark matter everywhere in the vacuum space?
We assume yes,
Okay.
it's present everywhere. Yeah.
Okay. The next question, I'm really interested in understanding the maths behind understanding the dark matter. Can you suggest some book or paper that can help him?
Okay,
I am not from a physics background.
you're
This
not
is a
from
question
physics
for me
back.
also.
Okay, so maybe I will give some references. I'll share with Jitendra, and then he can surely share with all of you. I'll just try to find out what are the references depending on the level, whether of the books that I would suggest. So yeah, I can surely recommend them for dark matter for sure.
The next question, what do we learn? What to do to learn more about cosmology in depth and to build a career in this field after completing mechanical engineering?
So after completing engineering, I think if you are interested in research, you can, if you're really interested to do like PhD degree, you can give exams for those. And just to have a basic understanding in cosmology, again, I can suggest some 2, 3 books for that. If you are not from a cosmology or astronomy background and you are still interested to know about these concepts, so I can suggest 2, 3 books. Again, I will share them with Jitendra, and yeah, a basic understanding. For example, in astronomy, you don't, I feel that in most of the cases, you don't need any specialization in the astronomy subjects. You need some command on the uh, physics subjects which are used in cosmology, the classical mechanics, the quantum mechanics, electromagnetic theory, all these mathematical physics. So you need a strong understanding of these core subjects, and then you can easily grasp the concepts of astronomy by going through some courses, some very good books, as well as if, for example, in Bangalore, there are these institutes which run this program where there is a 1 year coursework, and people with different backgrounds, not having any clue of astronomy courses in their masters, also come here and get the feel of what are the different fields of cosmology. So you can begin. I can surely share the references, and yeah, after BTech, I think if you're interested, you can also apply for short projects. You can check the websites of the institutes, particularly in Bangalore, who actively organize some short-term visiting programs also for masters and undergrad students, as well as this will give you an exposure to what is the research environment in these fields, what actually doing a 5 year research in these institutions mean. And of course, and if you are confident and prepared enough, you can uh, start or apply for a PhD degree in some of the institutes in India or abroad. So yeah.
Okay. What are the possible long-term fates of the universe under the influence of dark energy?
Okay. So yeah, again, this right now what we are observing is that the dark energy might get, because the equation of state is greater than -1, so might get weaker with time. So if it gets weaker with time, this accelerated expansion will also slow down with time. So there could be like I really don't want to say this, but yeah, there are people studying about theories that there maybe the accelerated expansion phase will not long, and then we will enter into a decelerated expansion, and the universe will move towards a collapsing scenario. But yeah, these are some extreme ends of the data, what data has to say. But the
Okay.
best fits are consistent with dynamical behavior of dark energy, which is undergoing acceleration. Yes, its energy density is diluting, but yeah, the expansion is still accelerated.
Okay. The next is, if dark energy is a property of space-time itself, does it have
Mhm.
entropy? And can it do work in a thermodynamic sense?
Yeah, you can. So, for example, dark energy, when we say that it is a cosmological constant, so the motivation behind that is that it is a property of the space-time itself. However, if you're working with other modified gravity theories or interacting dark energy models, where dark energy itself is some scalar field, then this perception of looking at dark energy would change. But yeah, of course, you can connect it with the property of the space-time itself and entropy.
Okay. How does particle physics, especially accelerator physics, shape the future
Hmm.
of cosmic research, especially when combined with quantum technology?
So again, so for this question, I would say that I'm really not the expert to comment anything about it. So I will maybe pass this question.
Okay,
So,
okay.
yeah.
Uh, how's the scope of cosmology nowadays?
Yeah, it is actually the very right time to work in cosmology, especially if you have a good, especially for people who have a good handle on data and statistical techniques, and also an interest in the different theories. Because as I also mentioned, so this is just for the dark energy part, but there are various surveys which are presently ongoing. So we are living in the time where a lot of telescopes are up there and they are giving us tons of data every day, and some of them will be operational very soon and some are still operational. And when we have a lot of data, there is a lot of work to analyze those data, to extract the correct information, and to work on the theoretical side, like think of the theoretical possibilities after seeing the trends in the data. So this is a really interesting time, very good time to work in cosmology, and thanks to the observational advancements that we have as of now. Yeah.
The next question, how can we definitively distinguish between an evolving dark energy field and modified gravity?
So yeah, interesting that this is what I have mentioned here. So this would be clear from some other observations, which have the imprints of how the growth of structures evolve with time. So it's like if the theory of gravity is not GR, it is something else other than GR, then there would be substantial growth in the predictions of those theory of how small fluctuations will grow to form the structures. So this information can be used to distinguish whether it is a modified gravity or not.
Okay. So the next question, if dark energy creates space-time curvature,
Hmm.
as it is present everywhere, then does the dark energy curvature taken as reference? So can we say that the whole space is curved? And actually curvature is done by other masses because we take dark energy curvature as reference.
No, actually, we have to see that dark energy. So I'll go back to the Friedman equation for this. So it's like the curvature of dark energy, the curvature of the space-time is shaped by all these quantities, like the matter, energy, and dark energy. So it's not that you have to take the dark energy as a reference. Rather, it depends on the energy densities and how they evolve with time. So when you talk about the very early universe, this dark energy component was really negligible. And the most dominant components were matter and radiation. So they shaped the geometry of the universe in early times. However, as the universe expanded and these components, their energy density diluted, it is very recently that dark energy has become the dominant component. So when we say that dark energy contributes 68% of the energy budget, this is the ratio at this is the percentage at present time. If you look at far past, this contribution was negligible, and that's why the you don't have to take the reference dark energy as a reference of space-time curvature. Rather, you have to see it that these different constituents will um, change the geometry of space-time depending on which dominates at what epoch. Yeah.
Okay. With DESI collecting such a massive data set, how do you
Hmm.
see AI or machine learning shaping the analysis of dark energy and dark matter patterns in the coming years?
So there is a lot of prospects for AI and machine learning, given the because of the large data that Daisy is collecting. And in fact, there are people working on these um, already. For example, people have also worked on reconstructing the equation of state. For example, here what I show is that there are different 5, 6 models of dark energy that have been fitted to the data. Another interesting technique is using machine learning to just use the data and without working with any model at hand. So it's being model agnostic and trying to see what is the behavior of equation of state. So the machine learning techniques are already being exploited heavily in these fields, and new techniques are being built up. So yes, there are very good prospects at present for ML AI for in the field of cosmology, not only for the DAISY observations, but many other cosmological observations as well.
Okay. You mentioned modified gravity models as possible alternatives to explain dark energy. Could you
Right.
briefly share how they differ from general relativity in predicting cosmic acceleration?
Yeah, so there could be some extra interactions. For example, GR is a minimally coupled theory, so we can have a scalar field which is also talking to curvature. So these are some non-trivial interactions between gravity and scalar field, which do not fall in the framework of general relativity, and they can help explain the accelerated expansion. So it could be a bit technical, but yeah, this is due to the extra interactions between a scalar field and the curvature that leads to um, modified gravity theories working as also explaining dark energy.
Okay. If dark energy makes up most of the universe, why is it still so hard to detect it directly? What's the
Be-
current leading theory about its nature?
okay, so it's because it doesn't interact with anything, so it's like it's very difficult to catch because it doesn't talk to anything. It, so it's like that's why it's difficult. Now, however, we still have a handle on it by, as we discussed, that by different observations, which are actually the distance measurements in cosmology from supernovae, from large scale structure, and distance measurement will contain the information of the cosmological model. That is how much dark energy is present and how it is contributing. So, yeah, we can't, though it is 68%, still we cannot directly measure it, rather in terms of the distances. And the present status is that the recent observations hint that this dark energy is actually evolving with time.
Okay. That means the percentage could increase with time.
Yeah, but in very future, so it's like presently the percentage is 68%. So this is what is consistent with. So even if it is 68%, the nature, what I mean by nature is that whether it is a constant or it is evolving in time. Yeah, these percentage would slightly differ, but not that much. That would be a very futuristic um, thing.
But Yashi,
Mm.
as a layman, I would be asking you that we studied that energy is neither created nor destroyed. So that means if the dark energy percentage would be increasing in future, in really far
It's
future, then would you think that some other form of energy would be converting into dark energy?
no. First thing, when I say the dark energy percentage, so percentage is it's the ratio to the total energy density.
Yeah, yeah.
So it's like the other energy density is decreasing because universe is expanding, and that's why the it's no so it's like it's not the creation of the energy, rather it's the percentage. So it's like at very early times the dark energy percentage was 0%. It was there, but it did not contribute to the total energy budget. It's a ratio. It's like the ratio of energy density of the component to the total energy density.
Okay, okay. So could dark energy reverse and cause a big crunch?
Yep, I mean, again, I would not say yes, but yeah, there are people who talk about these possibilities lying in some extreme ends of the data um, for some models. Yes.
Could dark energy dynamics emerge from quantum vacuum fluctuations or entropic gravity frameworks?
So when you say quantum vacuum fluctuation, okay, um, I'm not sure that I have. thought upon this or have come across, but um, already when we say that cosmological constant is there, this is actually the vacuum energy. The explanation is a vacuum energy. So yeah, the vacuum energy of the space-time is what we say that is the cosmological constant, and that can explain dark energy. However, as these observations are indicating that there are emerging challenges to that perspective.
Okay, okay. So, if the universe is expanding faster than light beyond our horizon, what does that imply about the limits of scientific knowledge itself? A very
What does it imply about the scientific knowledge itself? Okay, I don't know what to say for this question. Um,
I would rather say that in fact we are now learning more and more about the cosmology, more and more about the universe
yes,
itself,
right,
that we are coming to know that the universe is expanding, and the amount of
exactly.
dark energy, the percentage of dark energy,
Yeah,
the effect of
yeah,
dark energy, the effect of dark
mm,
matter on us, as well as
yes.
on the whole of the cosmology.
Right, right. And the data that we are receiving, I mean, from this limited source, and you call it a limited data, but it has a lot of information that we
For
still need to
us
process and
humans.
understand, yeah, for
Yeah,
to
yeah,
shape in
yeah,
our understanding of the cosmos. So yes.
yeah, yeah. Sorry to hop your question.
No, no, that's and thanks for that.
Which form of energy do you think is getting converted into dark energy? The same question which I asked.
No, no. So it's not any form of energy. When I say the percentage, it's the ratio of the energy density of dark energy to the total energy density. It's not something getting converted. So yes, there are interacting dark energy scenarios. These are also theories where people talk about interactions between dark matter and dark energy, where could be small energy transfer or momentum transfer. But yeah, again, there are various phenomenological theories. When I say the percentage is 68%, it's not that something is transferred from something else to dark energy.
And if I may ask you, Yashi, uh, dark energy is the energy which can pass through anything and everything, right?
Yeah, you can consider it, it presence everywhere. Yeah,
Nobody can feel it, nobody can catch it, nobody can
nothing,
see it,
nothing.
nothing,
Yeah,
nothing doing. No
nothing.
interaction at all.
No, no interaction at all. That's why it's difficult to catch it.
Yeah. But I think so. There are a few experiments which are going on to actually uh, catch the dark energy. What we say, the results of that experiments, uh, due to which the dark energy can be explained. I had seen a program on the Discovery Channel
Okay,
where they were bombarding uh, some particle. I don't remember which particle, but yes, they were bombarding, and they were trying to uh, know whether the result which has been observed was due to the dark energy. There is
okay,
something going on. I had
okay,
seen that program.
Ma'am,
So
okay.
are you talking about Sun one? This is
yes,
a different one. That
I
is a
think so.
different one.
Yes. Yeah.
Sun, ma'am, CRN one. But that is
Acha, you're
not
The
the
talking
same.
sun.
sun.
Okay, okay, okay. Okay, so is it particularly focused on dark energy, Sarge? I may not
No,
be
that
aware of
that
the
program
full
was based on
details.
dark energy and dark matter, so they were completely
Hmm.
talking about that only.
Okay, okay.
Yeah.
Okay, for dark matter, I can think of, but yeah, dark energy, maybe I'll check the reference that you're mentioning, and not that I am able to comment on it as of now. So yeah.
Are there any viable cyclic or bouncing cosmologies that reproduce the observed expansion theory without invoking a singularity? A very
So
technical
there,
question.
yeah, so there are various theoretical scenarios people study, but what is required is that when you that you have to fit all the observations at the same time. And when I say all the observations, these three particular observations like CMB, LSS, and the Type 1a supernovae. So phenomenologically, yes, people studied bouncing scenarios and all, but where it is only when you fit the theoretical predictions to the data to find the best fit values. So I don't know if there are well accepted bouncing scenarios which are consistent with all the cosmological observations at present. But yeah, theoretically there are, I am aware of. So it becomes difficult. For example, you have tons of model. So then you have to decide that what is the model of the universe. So it's like there are various model and you have to find the best model. And the best model is which is simple, elegant, and can explain a large number of observations at the same time. So this is what the simple lambda stereo model does. So of course, there could be phenomenologically motivated other models, but yeah, one needs to keep in mind that at the end of the day, you have to confront the observations and check the predictions of the theory. Yeah.
What happens to the universe if phantom energy with W greater than -1 dominates its expansion?
So if the greater than -1 dominates the expansion at present time, then the acceleration would be even faster than what is observed. So there would be a, so it's like the equation of state would be very negative, and that means the pressure would be more and more repulsive force would be present. That would lead to very faster accelerated expansion that then that is observed. So that would happen. Yeah.
So if dark energy keeps increasing, expansion accelerates uncontrollably.
No, no, ma'am. Basically, that is the answer of that above question.
Okay.
Let's go for today's question.
I'm sorry. Okay, so here we end the questions in the chat, and now I would take the questions personally. The participant can ask the questions. Shivam, kindly unmute your mic and switch on your camera so that you can ask the questions directly.
Sorry for interruption, ma'am. I would request Yashi, ma'am, please have your water, ma'am. Please have some water.
Sure.
You're just
Sure, sure.
1.5 hours.
No, sure. I had it. Thanks for reminding.
Yes, Shivam, you may ask your question. Kindly unmute yourself.
I have few questions about
Yeah.
topics.
Yeah.
The first,
Shivam, your voice is cracking.
Maybe you can type in the chat.
You can
Your
just
voice
type
is
in your
breaking,
chat
yeah.
so that I can read out the question because your voice is cracking.
Right.
Okay. So, does anyone else has a question?
is it good now?
Yeah, it's good now.
Yeah.
Ma'am, actually, I have three questions. One is of baryonic acoustic oscillations. As we know that they stop propagating, right, after the recombination. But what was the medium of their propagation? Like they are sound waves, so they can travel in vacuum, right?
So the universe itself was like a plasma kind of state, because in the early universe everything was hot and dense. So yeah.
And one about my quintessence. How
Quintessence, yes.
can you explain more about it, the energy fluid that it is, and the scalar field that it is? Can you
Yeah.
explain?
So if you have gone through, I mean, I don't know if you've gone through the courses in like field theory, simple field theory. So it's a field theory view of dark energy, where a scalar field is described by a where the dark energy is described by a scalar field, and which has a potential energy which dominates how it will evolve with time. So the idea is that it gives you a very like physical explanation other than lambda. Lambda is just a constant, whereas you can motivate quintessence by writing a Lagrangian of a scalar field, which has a kinetic and a potential term. And there would be an energy density associated with the scalar field and a pressure associated with the scalar field. And then you can define an equation of state, and you can work with potential like linear potential, quadratic potential. So it's like it gives you more handle to understand how this field actually emerges from a Lagrangian perspective. So this is how quintessence is, and it gives you an evolving equation of state. That is a W, which is a function of redshift, so it can evolve with time. So yes.
Okay, thank you, ma'am. And one about data that you have from.
Sorry?
Shivam, you are not
is
audible.
that there is some
Yes.
so why don't we just assume that the universe will end in a big crunch, and what more data are we looking about?
So we are looking for particularly the large scale structure data. Right now, we are just talking about the expansion history, as I mentioned, but there is a lot of information hidden in how these structures are distributed, like how these structures form with time, and they will give us the complete information about what is the nature of gravity, what is the nature of true nature of dark energy. One hint we have got that it may be evolving, but there could be various scenarios that could lead to that. So we are looking for more and more large-scale structure data to have, as well as supernovae data, to have a confirmation of our theoretical predictions.
Yes. Any more questions?
One more question,
Yeah.
that I'm really interested in cosmology childhood.
Okay, yes.
So what research topics work on?
What research topics to work on? So there are a wide range of research topics. So as I showed, the history of cosmological evolution. So there is a phase that you can study about dark matter, you can study about dark energy, you can study about the epoch of cosmic inflation, which is actually one of the very earliest epoch, which is very interesting because it is this epoch where the small fluctuations um, were laid down in the universe, which later on formed the large scale structures. So there is a wide range of topics, but the right way to approach is first to have an overview of the whole field, like going through some basic book which could give you an idea of what are the different epochs that we talk about. Good, like you can listen to some good talks about from some specialist person in different topics, which will give you a status of what is the current observational status of these research, like which field is more evolving in terms of where there is more data coming up, where theoretical models are being more tested and worked upon. So after going through this survey of your own, your search of your own, you can then decide upon what topic to work on in cosmology. Yeah.
Okay, thanks a lot, ma'am.
Uh,
And thanks for the amazing session. It
Thank,
was really good.
thank you.
Atulya is asking that he would like to know more about your journey into this career.
Okay, so
He's really curious about it.
okay, so so as I said, I did my master's from Banaras Hindu University, and in the master's, in the the third semester, we have to select our specialization. So where I chose space physics, primarily because at that point I was not really clear of which area in the whole astronomy to work with. I was also interested in astrophysics, and I learned about how stellar evolution, like how stars form, what are supernovae and objects like that. And slowly, I was also exploring my own interest. And it was not that I started with cosmology. And then I also did small reading project with a professor in Delhi University who worked in cosmology, where I got to know more about this subject. In the meantime, I also prepared for this exam, the GATE exam, the GATE JEST exams, which are the national level exams in India for getting admissions for PhD in institutes. And then in the meantime, I also read about cosmology, and I just got interested about understanding the universe and the theories which govern it. And after coming here in the first semester, we also went through a lot of coursework, which has strengthened our understanding of different topics. We had fundamentals of astrophysics, where a lot of astrophysics topics were covered. We also had specialized subjects like general relativity and cosmology. We studied about galaxies and all. So from all these coursework, as well as by attending different talks by the people who come here to give seminars or even online talks on YouTube's, I was re I my interest slowly shifted towards exploring cosmology, and this is how I started my journey from the second year of my PhD after completing the coursework. So, yeah.
I hope that answers your question, Atulya. And hope you can also choose some kind of a path which ma'am has chosen. Okay, so
Yeah,
now
please.
I would
Yeah, also please feel free to write to me if you have any suggestions.
definitely. You can share your mail ID on the chat,
Yeah,
ma'am.
sure, I'll do.
Uh,
Mhm.
and
Uh,
will we
what I'll do is, I'll just mail them your
Sure.
email
That
ID
would
and
be great. That would be
LinkedIn as
great.
well.
yes.
Yeah,
Thanks.
I
Thanks.
think everyone will be able to.
Okay. So now I would like all our participants to please switch on the camera for a group photograph.
Okay.
Everyone, please turn on your cameras so we could just capture this moment again. Okay. Everyone, please make it quick. I'm here, ready to take the. Don't worry about the mail, Lavanya. Basically, you'll be going to get on your register mail. Don't worry about it.